Good morning, AOBI. This is Mr. Dunning. Stand by. I have a math lesson for you. But before we get started, the bell work that is going to appear on the screen next is actually problem 12 from the quiz that you took on Thursday. I'm going to leave that same bell work up today and tomorrow, and you have to do it if you want notebook credit. To get started, you'll want to review lesson 4. Lesson 4, to find x. Today, we're going to be talking about tangents. And first, before we get going, you'll need a little bit of terminology. Okay, here we go. A tangent touches a circle in one place. If we have two circles, notice the tangent touches both. When we draw a line from the center of one circle to the center of the other circle, like that, we create the groundwork for a definition of internal and external tangents. Here's how that works. These two tangents drawn in the picture are external. The reason that we call them external tangents is because they do not cross this red line. We could also have tangents that cut across that red line. Those green tangents are called internal tangents because they cross a line in the center of one circle to the center of the other. So the terminology that we learned today: external tangents don't cross the line from center to center. Internal tangents cross that line. Today we're going to learn how to find the length of tangents to a circle. We're going to begin with an easy one. We're going to draw two tangents from this point to this circle. Now, in order to figure this out, we're going to have to use a little bit of earlier geometry. A radius drawn to a tangent is perpendicular to that tangent at the point of tangency. So those are right angles. If we connect this vertex to the center of the circle, we create two right triangles. This piece is equal to itself. That's the identity property. These pieces are radii in the same circle. That makes triangle 1 congruent to triangle 2, hypotenuse leg. And that tells us that these two tangents are equal in length. This gives rise to a couple of problems that you're very likely to see on tests. Speaking of tests, hold that thought. Last week, you noticed Monday, Tuesday, and Wednesday were lectures. Thursday was a quiz. That's a pattern that we are going to follow. The first 3 days will be lectures. The fourth day will be a quiz. That keeps our 75% notebook grade and 25% test grade how it should be. 3 days of notebooks, 75% of the week. 1 day of quiz, 25% of the week. 75, 25. Now, you know that you can pass this class with great notebooks and lousy tests. That's how it's designed. But you can't get past a grade of C without doing good tests. Okay, back to this. These two tangents here are going to be equal. So, what happens if we draw another circle? Same size, but down here. And a tangent from the same point to that circle. This tangent is going to be exactly the same length as this one and this one. You've already seen the proof that these two are equal. Well, if this circle is the same size as that circle, then these two are equal. So if we know the length of one, we know the length of all of them. If these two circles are equal, and pause with that thought, circles, like lines, are all the same shape. They're round. So the only definition or defining quality of circles being congruent is if they're the same size, because they're all the same shape, round. When they're the same size, we refer to circles as being equal, like line segments being equal, because all lines are considered straight lines and all circles are considered round. Shape is not an issue, only size. So if we say these two circles are equal and we know that tangent is 10, then we also know that x is 10 and y is 10. In example 2, we're going to rely on a little bit of trigonometry from earlier in geometry. Before we get to that, I want to review that with you. We're going to begin with an equilateral triangle. That is a triangle where all sides are equal and all angles are equal. Then in that triangle, we're going to draw an altitude here, creating two right angles there. Remember, altitudes are perpendicular to the base. This triangle and this triangle are going to be congruent. Here's why. This piece is equal to itself. That makes this triangle on the left, call it 1, and this triangle on the right, congruent hypotenuse leg. That means that these two little pieces here are the same size. Because triangle 1 and triangle 2 are congruent, this piece and this piece are corresponding parts, and so they also will be equal. We're going to use that take out half that picture, because if this angle is 60 and this angle is 90, that makes this angle 30. This is a 30, 60, 90 right triangle. And there's a relationship in the lengths of the pieces. Remember, this piece began as the whole base of the equilateral triangle, and this is half of it. So if the original pieces were each 2, then this piece here is 1. So we have a ratio. This piece is 1, and this piece is 2. The green piece can be found really quickly and easily using Pythagoras. The green piece, call it G, squared, plus this piece squared equals the hypotenuse squared. So that piece G squared equals 2 squared minus 1 squared. 2 squared is 4, 1 squared is 1, and that's 3. So G squared is 3, and G here, this piece, is the square root of 3. This particular triangle appears in many problems, and so it's worthwhile to remember the ratio. 1 square root of 3, 2. Because similar triangles are proportional, we put a multiplier out here, call it n. So if we multiplied everything by 2, we'd have 2 times the square root of 3, and 4. If we multiplied everything by 3, we'd have 3 times the square root of 3, and 6. We're going to use this now when we go look at how long a tangent is. If I make this central angle 60 and the radius 5, then those radii are both 5, and I start to see relationships here, because when I connect this point to the center of the circle, I have created 2 30, 60, 90 triangles. That means, remember, a radius drawn to the point of tangency creates a right angle, and that gives us 2 30, 60, 90 triangles. Now you know that the side opposite the 30-degree angle is going to be half the hypotenuse. So right off the bat, you know that this piece is going to be twice as long as that piece. It's going to be 10. This tangent here is going to be 5 times radical 3. You're saying, how did I get that? Well, simple. Here's how. The multiplier that we talked about, n, is multiplying the basic ratio so when we make n 5, we get these numbers. 5 times radical 3, and 10. These numbers here are the numbers that appear in this drawing. Using exactly the same trick, we're going to connect this point to the center. Our radius drawn to the point of tangency is perpendicular to the tangent. Now all we need is one dimension. That's it, 1. So if I tell you that the diameter of this, the radius of this circle is 3, then you should be able to fill in the whole rest of the picture. Each one of these angles here is going to be half of 120 or 60. That makes these angles here each 30. And again, we have a 30, 60, 90 triangle. And we know the short leg is 3, and this piece is going to be half of the hypotenuse. So we know the hypotenuse is 6. Once again, we're going back to our basic ratio. 1 square root of 3, 2. And we're looking at the multiplier. Well, this piece isn't 1, this piece is 3. So the multiplier here is 3. When we apply that multiplier to these numbers, we get 3 times radical 3, and 6. Well, there's our 3, there's our 6, and so the length of this tangent is going to be 3 times radical 3. So we've combined a knowledge of a 30, 60, 90 triangle with what we know about tangents. Quick review. Our radius drawn to a tangent is perpendicular to the tangent at the point of tangency. That means when we connect the point where they meet with the center of the circle, we have two right triangles. That allows us to solve if they give us a nice angle in here to work with, and often they do. if these are equal circles, let's see if we can figure out what happens with the length of this external tangent. Well, again, if we draw a radius perpendicular to the tangent, there, and there, we're off to a flying start here. And if we connect the centers of the circle like that, we end up with this bow tie here in the middle. Now, the one thing I know about this bow tie is that these are vertical angles, and they're equal to each other. Now, if we know that the radii of the circle are equal, say each radius is 2, then these two triangles are not just similar, they're congruent. Angle, angle, side. And that means all the pieces are equal. So if we know this piece, then we know this piece. If we know this piece, then we also know this piece. Now think for just a minute. In problems, they're not going to make it quite this simple. They're going to give you this distance here and ask for you to figure it out. You know, if that's the total distance, each one of these pieces is half of it. And from that point, you can figure out the length of this piece. Let's say that they tell you that this piece is 10. That makes each one of these pieces 5. And if we erase the part of the circle that we don't really care about, let's just get rid of some of this picture. We end up with a right triangle that has one piece 2, that's a leg, and a hypotenuse of 5. So if we call this piece here, this half of the length of the tangent x, then the relation is 2 squared, because this piece is 2, plus x squared those are the legs right there, equals 5 squared. 2 squared is 4. 5 squared is 25. So x squared is 21. And x is going to be the square root of 21. That's this piece right here. The whole internal tangent is going to be twice that long. there's an equal sign. So I want 2x because I want the whole length here. The whole thing. That's x, so I have two of them. 2x is 2 times the square root of 21. And that would be the length of this red piece, the length of the internal tangent. In review, today, we have learned what a tangent is. It touches a circle in one place. When we have two equal circles, and we covered that, equal circles are all the same shape, so the only criteria is size, and if they're the same size, then they're equal. In that sense, we pointed out that circles are like line segments because lines are all the same shape, they're straight. So shape is not a criteria, size is, and if they're the same size, we call circles equal. We talked about external tangents and internal tangents. And we talked about how trigonometry is going to play a role in determining the length of a tangent. We gave you some typical examples of finding the length of tangents. Tomorrow, we're going to keep on going with this idea, except we're going to add secants to the picture. Now, the relationship with secants is a little bit more complex, but not much. You can handle it. We'll see you tomorrow.